Okay, in this part of the tutorial, now we're going to generate the computational grid for the CFD simulation of a convergent-divergent duct. Okay, the geometry is ready. Now we're going to load the ANSYS meshing software. So I have already loaded the software. We have the geometry here. I'll make the view normal. And then I click on the mesh to make the general settings. So the first thing that we check is whether the physics preference is CFD, the solver preference is fluent, and then I decrease the element size to 0.1. Okay, let's adjust this window a bit and zoom. Okay, so now first the general settings. So I select this faces surrounding the region where the duct is located, and then I select insert face meshing. So this means that in these regions we will have fully structured grid. Okay, face meshing. And then I select the body containing the duct, and then I click insert method, and then I select a multi-zone grid with all quad cells. So it means that in this region we will have unstructured mesh containing quad cells. Okay, so this was the general settings for the methods for the grid generation. Now we have to do some mesh sizing and also some face sizing to finalize the meshing. Okay, so first I select the 4 top lines coming from the symmetry condition towards the region of where the duct is located. I click insert sizing, and here I use the element size. I put 50 cells. I want to add a bias so that the cells refine near the region of interest, and I use a growth ratio of 1.05. So in total 4 edges are selected with this refinement ratio. So we have to note that this one, the first line, is being coarser near the region of interest, so we have to reverse the bias for this one. Okay, the 4 are correct. Now we're going to the next edge sizing, which is the Alpha Streamline. So in total 3 lines, I right click and select sizing. I also here use the number of divisions instead of sizing. I put 43 cells. Also with a bias so that it refines near the region of interest. And then here I use also a smooth transition ratio of 1.05. And now we see this one and this one are correct. Finer near this region, but this one needs to be reversed. So I select the reverse bias, and for this line we reverse it. Okay, now this is also set correctly. Now we're going to the downstream lines, and then the same way we set the edge sizing. Here we put 80 cells, also with a bias, and then here for the smooth transition ratio I put 1.0354. Also here one of the lines needs to be, the bias for one of the lines needs to be reversed. Okay, this was also the downstream lines. And now we go to the remaining lines, which are the lines on top of the region where the duct is located and on its sides. Okay, so for these lines, so in total 7 lines, I insert sizing, and for these ones I use element size of 3 E minus 2, and then I change the behavior to hard. It means that I force the software to follow the sizing that I give it. So the software will not have any freedom to change the values in this region. Okay, so this was also the sizing for this region. Now we have to select the duct itself and also select the sizing on top of the duct walls. Okay, now I've also selected the duct walls and then insert sizing, and then along the duct I put the element size of 1.5 E minus 2. So this is also uniform, so I don't include any bias. Now we need a face sizing in this region because this region is not a structured grid, so we have to use also a face sizing. So I select the face, insert sizing, and here I use 2.75 E minus 2. Okay, so this is also the face sizing. The only remaining thing is the boundary layer grid that we want to have along the duct walls. Because along these walls, a boundary layer will be formed, and we're going to use lower noise modeling to resolve the boundary layer, so we have to use a boundary layer grid. Okay, so let's first select the body and right click, insert, inflation, and then for the boundary I need to select the walls where I want to have the boundary layer grid. Okay, the walls are selected, and then how to set the boundary layer grid. I do it with the first layer thickness, and here for the first layer I put 2.5 E minus 4, and I use 22 layers with 1.2 as the growth ratio. Okay, so the value for the first layer thickness should be set in a way that for the first layer we have a y plus below 5, so that based on the lower noise modeling technique we have a grid which is fine enough to resolve the viscous sublayer, so the inner sublayer of the boundary layer, so that at least we have one or a few points below y plus 5 to capture the velocity profile. Okay, so this is also set correctly. Now we did all the settings, it's time to generate the mesh and see how it looks like. Zoom out a bit. So we see the meshing has started, 5% already. So we have to wait a little bit before we can see the results. Okay, so now we have the result. So we see we have coarser cells here, and then it refines near the region of interest. So we have to zoom in to see how it looks like. Okay, so it's refined near the region where duct is located, and we have very fine cells in this region. This is what we want. Now we have to look to see how is the boundary layer grid. So we see we have the boundary layer grid starting from very small cells and then growing, and then what is important is not to have a jump in cell size from the last layer of the boundary grid to the surrounding cells. So what we see is almost a smooth transition from the last layer of the boundary grid. So let's take a look. So this is the convergent part, nozzle. This is the throat, and then this is the divergent part. So we have very smooth grid, and also here at the final edge. Okay, now let's also check the statistics. So we have 58,000 cells. Okay, this is good. If we check the quality, we can use, for example, here the skewness. And then we can see that the maximum skewness that we have is 0.61. And then by clicking here, we can find. Okay, so see, we have very few cells here with a skewness of 0.61. Typically, the skewness below 0.85 will not cause any divergence problem. So that should be no problem, but it's only a few cells. Okay, so then we come back to the normal view. So everything looks okay, and seems that we are done with the meshing. So as always, we save the project. And we close the ANSYS meshing. So here sometimes we need one update. And now by having the green tick here, the grid is also ready to be transferred to the CFD simulation solver, which here we're going to use ANSYS Fluent. In the next part of the tutorial, we will talk about how to set the simulation settings in ANSYS Fluent. So now we have it. We have the green tick here, and everything is ready.